evening. Welcome to the Design for AM Network event with a focus on 4D printing, design for 4D printing. And thank you so much for being here. So as you know, and as you can see on the program, we have 6 talks on the different aspects of the design for 4D printing. And we have also 2 panels after each panel after 3 talks. And yeah, so we can straight away go for the first talk, right? So Dr. Ali Zolfagharin is with us as a first speaker. Ali, can you hear me?
Yes.
Okay, yeah, so let me very briefly introduce Ali. So Dr. Zolfagharin is from Deakin University, Australia, and he's co-founder of the 4D Printing Society. And he's here, and we are very interested to learn more about his pioneering activities on the 4D printing, design for 4D printing, with the focus on soft robotics. So Ali's talk title is Crafting Tomorrow's Robotics by 4D printing. So Ali, go ahead and talk about a bit yourself, and also you have 20 minutes to kind of share your achievements with us.
Thank you, Mahdi. Sure. And could you please tell me, do you see my presentation slide in the
Yes,
presentation?
yes.
Great. Good. Thank you, Mahdi, for introduction. And I'd like to thank the organizers for this event and having me here in order to promote the 4D printing further to the public and also to the experts in the field. Currently, I am with Deakin University in the School of Engineering in Deakin University. We are based in Geelong, which is the coastal city nearby the Melbourne. It's 70 km from the Melbourne, and we are based in the Warmpong campus. Here it is our 4D printing and robotic materials lab in our cadet building in the Warmpong campus. And recently, I've been honored to receive the Australian Research Council fellowship on the 4D printed materials for soft robotic applications. And also I'm part of a bigger society that is the 4D Printing Society. 4D Printing Society comprises of more than 40 institutes and universities from more than 16 countries, which we are with our colleagues, we are working on frontiers of the 4D printing and smart materials in additive manufacturing. And what is 4D printing in general? If I'm going to define the 4D printing, it differs from the 3D printing in terms of the materials used that we use, the stimuli responsive materials. They are responsive materials which change their properties, shapes, functionalities in response to the external stimuli like the electricity, magnetic field, light, humidity, and temperature. And the 4th dimension, of course, refers to the time that it differs the object and structure made with the 4D printing from the 3D printed structures. There are different applications of the 4D printing we have so far worked in our lab and in collaboration with our colleagues. For example, in soft robotics as a soft grippers for manipulating the fragile organs, or in bioprinting for printing of the soft actuators and lattices and cells, and we also name them as a 4D bioprinting. In medical processes for flexible manufacturing and person-specific manufacturing, and also for the sports like the shoe insole that can be adapted for different application of the users, and a structural composite for the energy absorbing of the materials and structures. Also as a sensor, flexible sensor, soft sensors with the biomedical application for with having more conformity to the bodies and the organs and tissues, and recently as a vibration absorption and isolation for some industrial and automotive applications. Out of this, I'm mainly focused on the soft robotics, as you were from the title of the talk today about the 4D printing application in robotics. This is one of our earlier work in 2016 that we named it at that time evolution of 3D printed soft actuators. And now we mainly focus on the 4D printing that we thought that it's good to manufacture the soft actuators as part of the robots manipulator using the 3D printing so that it would be more cost efficiently and also time efficiently, and also we can come up with some intricate geometries that we couldn't achieve using the conventional methods. And two things we addressed at that time. One was the processability of the materials that could be 3D printed, and also smart materials or stimuli responsive materials that we needed for this application. And this is one of our earlier work during my PhD. In early years of my PhD, I've done on that just we use the polystyrene film as a substrate because of its TG or glass temperature it has as a thermoplastic, and then we printed some hinge with using the hydrogel with different color in order to absorb more light, and irradiated IR or infrared light on that, and then you could see that from the hinge the bending could achieve based on the thermoplastic behavior of the polystyrene film. And this was one of the running work in terms of the 4D printed origami that we could achieve. And then this work evolved so far, so that recently with our colleagues in the University of Nottingham and with Nottingham Trent University, we come up with this idea of the 4D printing of the soft grippers, as you could see, using the 3D printing processing parameters like the velocity of the nozzle or how fast you're going to do the 3D printing at different layers, and also the different patterns that you could use in order to achieve the bending in the soft actuator or soft grippers. This is still based on the 3D printing or 4D printing processing parameters and shape memory polymer behavior of the materials used. And also this is the another work that during my PhD we have come up with in using the polyelectrolyte hydrogels. And we 3D printed hydrogels, particularly chitosan at that time. And then the optimization was quite burdensome. We needed to come up with some coagulation after the printing, and also optimizing the parameters like the pressure, speed of the nozzles. And then the physics behind that was in the multiphysics. We immersed the hydrogel into the electrolyte solution. We applied the electricity on these electrodes, and with the based on the Donan effects, the number of the ions entering to the one side of the rail was more than the. Let me bring that pointer that might help better. The Suling occurs at one side of the hydrogen more than another side due to the Donan effects, and leading to the osmotic pressure buildup at one side that leads to some bending behavior. And it was reversible. With changing the polarity, we could get the reversible behavior. And still this work is evolving, as you could see in some of colleagues in South Korea recently developed this type of the gripper using the chitosan, and also adding some nanoparticle materials as a cargo gripper for some biomedical application. And in another work, we come up with the idea of heterogeneous 4D printing. I've seen earlier this type of these terms from another colleague that you will see is talk later after me from Frederick Demoli. I think earlier coming up with this term that I like that heterogeneous 4D printing. That we use the 3D printing for some part of the robots, and then we use some actuators externally to add that. In our sister lab in Nottingham Trent University, we developed this idea, and then we added shape memory alloy, and then we used the 3D printing parameters for getting the different stiffness, as you could see, different payload, and then different sizes we could achieve with this sort of the soft robotic application in 4D printing. Indeed, that is the heterogeneous 4D printing we name. In our other recent work, we developed this two layers or multi-material. This is better than the two layers for 4D printing with tunable bending that we use again shape memory polymer, and also we use TPU like the Vero and Tango or Agulus, that is instead of the Tango recently introduced as an elastomer. We printed at two different layers with different thickness, and then we could achieve different bending angle based on the height of the layer, and also changing the printing parameters as a gripper. And also we developed that simulation part specific to that 4D printing of these two layers in order to reversely be able to predict the bending behavior of this composite 4D printing material that we achieved. And we successfully showed the application. For example, again, in the fragile objects that you could see in the glassware in the lab, when we applied this gripper and then we heat it up, and it start bending, and it could work as carrying this payload. Even using the conventional robotic, we bring these soft grippers or soft actuators using 4D printing as an application. Also, we could we name that pneumatic-based actuator as a 4D printing. As you could see, easily at applying the compressed air, you can get some sort of the bending. Again, the printing parameters matters here in the amount of the bending and the force that you will get at the end. This is a TPU material that is 4D printed, and you could see for soft objects like the football or some other applications that like the fruit harvesting, so that you can use this sort of the materials that are other application of the pneumatic soft robots using the 4D printing. And we were able to develop the silicon, and that you will see in the later slides using the 3D printing. Is not quite a straightforward application, but using the EcoFlex and Silicone A and B, we could achieve some sort of the 3D printing of the silicon, and with adding ethanol based on some of the earlier work of the other colleagues in soft robotics, we could develop these parallel robots. It's one of the few parallel robots using the 4D printing, earlier parallel robots, that we use the parts of the robot using the PLA, like the static parts, the bodies, and conventional parts. But for the actuation, we use this 4D printing of the soft actuator or silicon-based soft actuators. As you could see, it is electrothermal. The wires are nickel chrome wires is inside of this silicon-based soft actuators, and with applying the electricity, it heat up and expanding because of that ethanol that are entrapped into the silicon. It leads to some actuation. This is another work that we name it like the bio-inspired 4D printing. We come up with this shape that you could see as a torsional spring, and inspired by the image that you could see on the left, and we come up with this sort of the joint for a soft gripper, and this add more compliant so that you can grab like the strawberry and some other soft materials we could pick and place using this sort of the printing for the printing grippers. Also, there are some other application of the 4D printing in soft sensors that we could develop, and then we use some nanomaterials and then 3D printed them, and adding some conductive material, as you could see, and they have good self-healing properties, and also some acceptable conductive properties that could be used as a sensor for the application in the biomedical application for heartbeat and so on, that you could think about. And this is the silicon 3D printing that I talk about. We modified one of the common 3D printers in the lab, and we could do the silicon printing. Indeed, our main novelty in this work was using the nozzle, and we used some CFD analysis in order to come up with the nozzle that we could have the most optimized performance in terms of the extrusion and rheology of the silicon. And then the optimization have been done in order to achieve the most optimized strength from the silicon. And then the interesting point of this work was that you could see using the 3D printing, we could get the strain and that we were not achieved using the molding. This is the black graph you could see is just using the casting of the silicon, and because of the alignment of the silicon in the 3D printing, a higher amount of the strain could be achieved that you could see here in just in this instrument machine how this elasticity is shown. And also we could do that after developing that 3D printer. We could develop this sort of the pneumatic actuator again, just purely based on the silicon ecoflex. And the other application of that for the biomedical application of using silicon was proposed in that work as well. And having developed that silicon, intentionally stay quiet so you could hear that we brought that application to robotic, that you could see with a human robot interaction with different shapes, and bringing that deep learning, we could develop this sort of the robotic modules to interact with the human. And also again, still we keep using of the silicon as a pre-strain for developing a different soft gripper by inspired soft grippers that you could see they are pre-strained, and they have bistable mechanism that we could achieve using this sort of the actuators. And non-assembly 3D printing of the joint is another application of the 3D printing as soft and 4D printing is soft robotic, that with one step we could develop the robotic arm and the joints that are printed just in one step that you could see, and then you could add the actuators or cable for your purpose. And variable stiffness is our other works that we are working recently on it. With variable stiffness joints, we could get the changing just the joints material. You could see we could get different trajectory of the grippers or the muscles. And also, again, with our sister lab in Nottingham Trent, we could develop this sort of the soft actuators with using the 3D printing parameters. We could harness different stiffness in order to make a trade-off between the bending and the force at our endpoint for pneumatic actuators. And recently in the project of my PhD student, we could apply the AI control 4D printing mechanism. As you could see, we use the shape memory polymer and the 4D printing of shape memory polymer in order to achieve different stiffness of the joint. In robotic application, we just use these flexible joints here, and then with using the 4D printing, we could come up with different stiffness, and with changing the properties of the spring or the joint, we could achieve different stiffness for different application in soft robotic. And the novelty of this work is bringing that reinforcement learning into this 4D printing as soft robotic application of the joints. As you could see, it has some application that we envisage for some medical applications and prosthesis and wearable application. And apart from the shape memory polymer, we also use that ethanol and silicon ecoflex one that you earlier seen, and we developed this rotary 3D printing for this silicon application, and then we use that in that flexible robotic that you could see, we could control the stiffness of that joint, and also we could achieve this reduction in the amplitude of the vibration. That was the main novelty and focus of us in this work, that with changing the stiffness using the 4D printing, we could achieve different vibration behavior of the system. And we're working on that to apply that in different soft joints and muscles and so on. I think I'm getting closer to the end of the talk, if I'm not already not past that. And this is what we are going to do in future, is our recent work and idea of the sustainable robotic that we are going to use the 4D printing for more sustainable robots and reduction of the waste. And we come up with the different materials that could be used for this, and also the further application of the 4D printing in biomedical application, like the tremor suppression and the cancer therapeutics studies as 4D printing and the micro robots could have applications. And our two earlier books that in 4D printing we already published, and this is our third book that is more relevant to this talk, is for robotic materials, and will be published in 2024. And these are our collaborators, and that you could see here, they help us in this works that I just present. Yeah, thank you, and sorry for this if it was a bit rushed. I tried to bring more relevant materials related to robotic to this talk. Yeah, thank you, Matty, and everyone.
Thank you so much, Ali, for your great presentation. Lots of information in just 10 or 15 minutes. Thank you. So as you know, there's a Q&A at the end of each talk, and you can ask your question by raising your hand, or you can write in the meeting chat box. So here we have an opportunity to talk about the challenges or any comments that you have on Ali, at least Ali's Ford or other works related to the Ali's. So, yep, any questions? Yep. Yes, we have two questions from the Vail and Rahimi. So, Vail, go ahead.
Thank you so much, Ali, for the nice presentation. I just have two questions, if you don't mind. The first one is about the material that you used in order for you to control the stiffness, to reduce the vibration. So that's my first question. And then the second question is about, have you seen a good uptake from the industry accepting 4D printing in general? What was that strongest industry that liked the idea of 4D printing, basically? Thank you.
Great. Okay, thanks for the question. Yeah, the materials, we use two different materials. One was shape memory polymer, that was PLA, and then we used the carbon fiber for conducting the heat from the electricity and converting to heat in order to reach to the glass temperature, and we get this springiness from the joint. Another material was the silicone and the ethanol entrapped into the silicone that leads to some swelling when it's heated. And this was for the first question. And second question, I think we are going to discuss about that in our panel talk about how we could relate this 4D printing to industry. If you don't mind, we will discuss that there in more details.
Absolutely. Great. Thank you so much.
No way.
Thank you. And we had Rahimi with the hands up, but there's another question in the meeting chat box. So Mohammed said, how reliable is AM of EcoFlex in terms of 3D printed structure stability, and what remains as a challenge from your experience?
Yeah, very good question. Yeah, it is still challenging. There are different companies are working on that currently. The price is quite high, and having the support material is challenging. And because curing these two A and B, especially two-part silicon, is challenging because it takes time. Faster curing is a matter of the challenge. Currently, we are working on that. It takes quite time, and yeah, that support materials that will be used and then print for different intricate geometries. Another challenge of silicon theory is very interesting ongoing research on this silicon prototyping. Still, there is a room to work on that. Yeah.
Thank you. And I can see the Vail has a hands up. Vail, do you have any other question?
No, sorry, I had it up since earlier.
Thank you. So, any other questions in the meeting chat box? So there's another question, Ali, from the Pradeep. How do you measure the variable stiffness?
Yeah, we use the small instrument machine in our lab, and then we applied in terms of the different lengths of the spring or joint that we achieved. We already, before doing the test, we tested that in terms of the force displacement to get that stiffness gradient. And then when in the work, we based on the displacement that we achieve, we relate that to that stiffness.
Thank you. And there's another question from the Duru pattern. What kind of modifications you apply to the 3D printer for, printing the silicons?
Yeah, we use syringe pump. We use syringe pump, and then we use just XYZ Cartesian movement of the printer, and then we use syringe pump in order to control the rheology and the pressure of the extrusion.
So I assume it's affordable, right? It's not very expensive.
No, it is very lab. It's one of the cheapest, I think, silicon 3D printing you could do currently in the market.
So yeah, there's another question from John in the meeting chat box. So to make this sort of technology more widely used, what additional design tools do you think are required?
What technology? The 4D printing in general?
Yeah, what kind of additional tools do you think is needed for advancing this technology?
I think currently that multi-material 4D printing is the focus. Different angles of the printing is adding, like the rotating, the arm, and robotic 3D printing that is adding more dimension to the 4D that we could control. And I think our main current challenge in the 4D printing still is the material aspect, and more chemistry and polymer aspect of the material is more required for 4D printing.
Okay, Baylan, thank you. There's a question regarding the space. Is a general question, but we can also we have a similar question that's going to be asked in panel. But can we narrow it down to your research activities? Or where do you see things that your print have application for the aerospace or space, or like solar panels?
There could be some application there, especially in terms of the reducing the weight, and also deploying the structures that are, for example, flat, and then like the antenna or solar panel, and then they need to deformation or changing them or morphing when they are deployed, and they are helping with the reducing the weight and efficiency in the fuel, and these sort of the things that 4D printing can have advantages there.
Okay, brilliant, thank you. And there is a question from Alan regarding the consistency of this kind of activation, how reliable they are when it comes to the activation of the materials.
There would be some hysteresis as well, but this could be predicted. When you could do the test and repeat the test for a number of the times, you know that how they are decaying after losing the performance. This is one thing we could do, and we are still working to improving that. For example, pneumatic one or hydraulic one is more repeatable. They have their own challenges as well, but there's a compromise that which one you're going to achieve and which one you're going to lose.
Yeah, I think also a closed loop control might be the solution. So when you monitor and then you have a feedback, and then according to the feedback, you can activate the system gradually.
Yeah.
Okay, thank you. You have 2 minutes until the next talk. We have more questions. I can see another question. Yeah, we have more than 1 or 2 questions, but let's answer the question from Kartikeya. So how are the functional 3D printers different from 4D prints? The finger gripper printed by TPU would be considered to be functional 3D print.
Yeah, we use that new, and that's again a question that may arise from some people. We use that pneumatic as a stimuli. We are not limited to like electricity or magnetic or anything that as an input that the external stimuli we can consider it as a 4D print. And then we come up with using the 3D printing processing parameters, like the different design, different patterns, different layer height, these sort of the things that we can control the bending or force coming off when we are applying that input, that is the air pressure as air here, for example. So this could be 4D printing altogether. It's something that is related between the processing parameters of 3D printing and external stimuli, and then you can get the changes in the product or structure after 3D printing. So the synergy of these three things, we could name it as a 4D.
Okay, brilliant. Thank you so much. I think there are more questions in the meeting chat box, and then
I
perhaps
try
after
to address
this,
them as
yeah,
I try to address
after
them in
this.
comments. I think if I could.
Brilliant.
Yeah.
That's very kind of you. Thank you so much, Ali. And